show your mean, mean pride.
Hi, and welcome to today's lesson on transformations of logarithmic functions. Over the last few days, we have looked at sort of introductory material related to logarithmic functions as far as introducing what the graph of a logarithmic function looks like and comparing it to an exponential function. One thing we have noticed is that an exponential function, its inverse is actually a logarithmic function and vice versa. We've also talked about logarithmic laws and properties of logarithms, so we're going to kind of tie all of that in into graphing transformations today. Just a few things as far as comparisons go between the graphs of an exponential and a logarithmic function, just as a review before we look at the lesson for today. So as far as graphically, we see that, again, with a logarithmic function, it is in fact the inverse of an exponential. So for no specific base here, y equals a to the power of x. If I do a mirror image of that through the line y equals x, I do get the inverse, which is a log-based function, y equals log base a of x. Comparing the properties of those functions, so we'll notice for the exponential, we've seen in the past the domain is all real values of x. Its range would have to be all positive values of y, since there is a horizontal asymptote at the x-axis. The intervals where it is increasing, well, that function is always increasing, so between negative infinity and positive infinity, that would be true. As far as where is it decreasing, the function is always increasing, so it will never be decreasing. The asymptote, as I mentioned, is y equals 0, the x-axis, and the exponential graph does not have an x-intercept, but it does have a y-intercept in general of 0, 1. Comparing that with the log function, the domain of that is actually restricted because there is a vertical asymptote, as you see later on in the table, at x equals 0, but by consequence the range is all real values. So the domain and the range are almost the opposite, comparing the exponential to the log-based function. Similarly, the function is always increasing and is not going to be decreasing at any point. And unlike the exponential, there is an x-intercept at 1, 0, but there would be no y-intercept. Now, as far as general strategies for graphing a transformation of a logarithmic function, so we're going to be considering log-based functions of the form a times log base b of k times x minus d plus c. So the coefficients that are present in this this basic formula are familiar to us just from basic transformations of any type of function, as we've seen in the past. So the value of a will act as the vertical stretch factor. Keep in mind, if a is negative, there is reflection across the x-axis. The k value would be the horizontal stretch, or will tie in with the horizontal stretch factor, I should say. The stretch factor will actually be the reciprocal of k, so 1 over k. Keep in mind, if that is a negative value, there is reflection in the y-axis, and then d would be your horizontal translation and c your vertical translation. So all of these concepts are familiar, we're just now adapting them to a logarithmic function. Right? Now, as far as the order that transformations should be performed in, that is no different. We should still perform stretches, reflections, and then do translations last. Now, as far as basic process for graphing a logarithmic function, what we should do, what would make the most sense would be to actually start by graphing the base logarithmic function, which, again, depending on what your base is, that will vary, but whatever the base is, you'd want to start with that. Now, you may actually, in order to help you with that first step, kind of recall the fact that any log-based function is in fact just the inverse of some other exponential function of the form y equals b to the power of x. So you may want to actually start out by graphing, or at least visualizing, some points that the exponential function that you're trying to take the inverse of to create your base log graph, what that would look like, and then actually produce the log graph you need. Again, you just have to picture switching the x and y coordinates of the corresponding exponential that the log-based function is the inverse of. Once the base is actually plotted, then it's just a matter of applying the appropriate transformations, and again in the correct order: stretches, reflections, and translations. So we're going to look at some examples where we can actually incorporate the ideas just mentioned. So in each of the examples that are to follow, we're going to graph the function and then also state the domain and range and any asymptote present for each function. Now, considering the first one, y equals log of x minus 1 plus 5, one thing we do need to realize from this equation, it's implied, but we're working in base 10, right? The 10 is typically not shown, as we've seen before, but is implied when you just see log, right? Now, what we would want to address next is any transformations that would need to be produced here. Now, we're going to list the transformations first, but then we'll also want to consider, what our base function is. Now, we could list that right now. So the actual base function, we're going to be picturing, well, the exponential that we're doing the inverse of is 10 to the power of x. So we'll want to picture, what we would want to start out by graphing is y equals log of x, right? And then below, we're going to list the transformations that will need to occur of that function, right? So as far as the transformations of log of x that we will need to perform. So the transformations of y equals log of x that we're going to need to perform. Well, the first thing we would need to do, as it turns out with this particular function, there really isn't much to do other than a translation. So the thing we will need to do to our graph of log of x is to actually recognize that, well, because I see x minus 1 in brackets, I'm going to have to translate right 1 unit. And with the plus 5 at the end of my function, that will mean I will have to also translate up 5 units. Okay, so once we have the base graph created, we'll have to keep in mind that we are going to need to perform a translation, right 1 and up 5 units. Now, as far as just picking and thinking of some points that we could, produce to create our base function, well, we'll pick some values of x to work with. So I'm going to make, in my table for, again, we're going to start with the exponential function and then take the inverse of that to produce our log of x graph. So I'll pick a few values of x that we could try. Now, because this is base 10, we're going to find that the values are either very small or very large rather quickly. So picture if x is negative 2, 10 to the power of negative 2 would actually be 1 over 100, or 0.01. Okay? If x was negative 1, I would end up with 1/10, or 0.1. If x was 0, 10 to the power of 0 is 1. 10 to the power of 1 would be 10. 10 squared would be 100. Beyond that, we're going to have a very difficult time plotting points that big unless we have a very flexible scale. So we would be advised to just sort of leave it as is. Now in the table for the log-based function, I'm going to make a column for the x's and the y's, but literally all I'm going to do is picture taking, for instance, just starting with this first set of x and y values from the 10 to the power of x function that we've produced points for. I'm literally just going to exchange the x and the y values. So I'd have 1 over 100, that would equal negative 2. So then similarly 1 over 10 as my x would produce a y value of negative 1. If x was 1, y would be 0, and so on. Right, so what we'll now be using, we're actually in our table, picture, this is what we're going to start out with as far as our base graph. So if I can plot as best I can the points that are in that table, I'll have my base function created. So below, we're going to do that. So what we'll do, we see on the grid here, so we're just going to plot the points that we're able to accurately graph from that table. Now, one point in particular that would definitely work would be, or that would be fairly easy to graph, would be the X-intercept, which is at 1, 0. So I know right there I have a point. I also know that when x is 10, according to my table, y would be 1. So I would have a point over here. Now keep in mind, if I had the space, I would have to go all the way to 1,000, for instance, to be at 3 vertically. I'd have to go all the way to 100 to be at 2 vertically. So we're definitely not going to have the space for that. Also, as my value of x gets smaller and smaller, I get more and more negative. So if I kind of pictured, what 1/10 for x would be, that would be technically where I'm -1. But the basic behavior of the graph is going to be that it heads towards its vertical asymptote, which is the y-axis, okay, on the left. And then I know I'm just going to connect to my point at 10, 1 on the right. So that would be, if we're labeling the function, that is y equals log of x, right? So then all I need to do to that graph to produce the function we're actually being asked to graph here, if we go back to the list of transformations again, all we need to do is translate that function right 1 unit and up 5 units. Right? So what I'll do, I have 2 particular points of reference that I can use. Now the one point of interest would be the x-intercept. So picture if I take that 1 unit to the right and 5 units up, I would end up here. And the other point that I actually had in my table, if I went 5 units up and 1 unit over, I would technically be off the grid, but I can kind of picture roughly where that would be. One other thing to consider here, because I have translated this function to the right, it does have a vertical asymptote already. So I'm going to picture it used to be the y-axis. So it might be useful at this point to envision, well, 1 unit over, if I translate, so on the left as I get closer here, the function would have to look like that. And on the right, as it approaches the point on the right, I would have it, again, rising but fairly slow, just based on the fact that I'd have to go a lot further out to move up very far vertically. So the equation there of the function, now that we have graphed sort of in the end, would be log of x minus 1 plus 5. And we have completed our graph. Now, the only other thing we were asked to do that we haven't already done in this particular question is we needed to state domain and range, and we need to state also where the vertical asymptote is. So for the domain, now based on the fact that I have translated the graph, now I can see that the graph does not cross or touch the barrier set up at x equals 1. So my values of x must be greater than 1 and must exist as a real number. My range, well, with a log-based function, doesn't matter whether I translate up or down, left or right. The range will be all real values. That's not going to change. So I have y existing for all real values. And lastly, the vertical asymptote. I do have a vertical one in this case. So the vertical asymptote is, and if I list its equation, is x equals 1. Next example. So this one, similar to the last one in that if we look and identify right off the bat what the base is, again, this is a base 10 function. So similar to the last question, really will be no different as far as, we might want to picture the exponential, y equals 10 to the power of x, to help us produce the log-based graph that will act as our base, which is log of x. Right? So literally, we could use the exact same table as before. I will quickly fill in the values just so we have them as a reference, but we would be able to use literally the same thing. Okay, so again, we can use the same values as before. And what we should now do, we will graph that function again momentarily, but we want to identify any transformations. So again, the transformations will be of y equals log of x. Now, what we might want to do, if we're picturing with this particular function, one thing we did not have to worry about in the first example was the coefficient on x. In this case, I actually have a 2 in front of that. Okay, now from past experience, we have seen anytime the k value is not already factored out, we should do that. So what I'm going to do is I'm going to rewrite that equation as y equals log of 2 times, and then I'm going to have x plus 3 minus 1. Right? What that now indicates to me is clearly what the k value is and what my horizontal and vertical translation are going to need to be. All right? So as far as transformations of the base function log of x, first thing I would need to do is address the fact that k is 2. So what that would actually do to my function is I would have to stretch the function horizontally by factor 1 over k. Now in this case, because k is 2, my stretch factor would have to be 1 over 2. And then once I've performed that transformation to my base function, the next thing I would need to do is address the fact that, well, there are translations here as well. So I would need to, according to what's inside the brackets, translate, this would be left 3 units. And because of the minus 1 outside of the brackets, I would have to go down 1 unit. Right? So similar to the last example, we'll start out with the base graph and then go from there. So we've got log of x graph to start with, and now we're going to perform the 2 transformations that we outlined above. The first one being, to recap, I have to stretch my function horizontally by a factor of 1/2. So if I take sort of the 2 points that I graphed clearly as a reference here, my original x-intercept was at 1, 0. If I stretch that horizontally by a factor of 1/2, that means I have to take the x-coordinate of that point and multiply it by 1/2. So it would now be located at 0.5 and 0. Similarly, if I take the point that was at 10, 1 and stretch it horizontally by a factor of 1/2, it would now be at 5, 1. Right? Now, as far as any other points, we'll just have to sort of approximate them, but our graph will approach the y-axis a little bit more rapidly now that I've compressed it horizontally, and I will be able to show a little bit more of the graph to the right of the point at 5, 1. So if I sketch now what the curve is going to look like, it's going to have to look something like that. Now, as far as the equation of that function in green, this would have to be y equals log of 2x. Now, whether you put the 2 inside the brackets or outside at this stage really does not matter. When I do the next step and actually perform the translations, it will become more of an issue. Right? Now, keeping in mind what we now need to do, our function in green, is to translate it. So I'm going to translate left 3 units and down 1 unit. And we did see in the previous example, when I translated horizontally, that actually shifted my vertical asymptote. So what I'm going to do again here is realize, well, if I'm going 3 to the left 3 units, what I need to do is envision the vertical asymptote no longer being at the y-axis, but actually being 3 units left of that. So I'm actually going to draw in a line at x equals -3, just sort of as a reference, so I know my function cannot go through that vertical line or past it through the other side. Right? So then if I take each of the points that this particular function is going through, that I have at least accurately graphed now, and I move them 3 left and 1 unit down, the function I will get, so if I picture 3 units to the left, 1, 2, 3, and down 1, what was my x-intercept before is now at the point -2.5, -1, and then my other point, which was before at 5, 1, would now be at, so if I went over 3, would be at 2, and actually now the point I have is a new x-intercept, as it turns out. So then, what I would do from here, basically I have to connect those 2 points, and then I know the behavior of the function beyond that. Okay, so there would be my final graph, and if I was to write the equation to represent that, this would be log 2 times x plus 3 minus 1, as we had illustrated earlier. As far as, just to tidy this question up, what the domain, range, and the asymptote are, well, the domain, based on where I had to move the graph, now the function has to have x greater than -3. So my domain is x greater than -3 and a real number. My range does not change. It is, again, all real values of y. And then the vertical asymptote is, and it would be x equals -3. Notice the connection between the value of my asymptote and the value that comes up in my domain. All right, now with the first two functions that we've actually graphed transformations of, in both cases they were base 10 logarithms. What we're now going to look at are some functions that actually include different bases. And as we're going to see, sometimes it actually makes more sense to actually apply one of the logarithmic laws we have talked about to help determine specific transformations, rather than necessarily interpreting the equation as it was given to us originally. All right, with part C, so the function we're now considering is y equals log base 2 of 8x. So, a few different ways we could look at this. The fact that it is base 2 is important. Now we could interpret that as, okay, I could draw the graph of log base 2, and then the fact that there is an 8 multiplying the x, I could say, okay, well that is a horizontal stretch of the function, but the problem might be that if k is 8, my horizontal stretch factor is actually 1/8, which chances are would not be that easy to illustrate very effectively. So rather than doing that, what we could try instead is to actually incorporate one of the log laws that we've seen. The fact that there is actually a product occurring within the logarithm, what we would be able to do here, if I wanted to envision another way of writing that function, I could actually use the product law of logarithms, which says if I have a product of two expressions within a logarithm, I could separate them into a sum of individual logarithms. So actually y equals log base 2 of 8 plus log base 2 of x is actually equivalent to the function that we have, right? Now what I would focus on from here is the fact that, well, what I'm doing the logarithm of here, 8, happens to be a power of my base, which is 2. So what I would do from here is just simplify a little bit further. So I've got log base 2 of, well, 8 is actually 2 to the power of 3. And I still have the log base 2 of x at the end. But the nice thing about what I've now done is I can actually look at the expression here, which says log base 2 of 2 to the power of 3, and just recognize from another law we've seen that that should simplify to 3. So in the end, my equation for y is in fact log base 2 of x plus 3. Now as far as comparing that function to what we had sort of initially thought, you know, a horizontal stretch, I think the fact that what we now have log base 2 of x plus 3, which really all I need to do there is perform a vertical translation, that will be much easier to do, right? So as far as transformations of y equals log base 2 of x, which is the function we're being asked to graph, literally all we will need to do here is translate up 3 units. Much easier to do. So what we'll do, like we did in the previous example, we'll start out with, it might be easier to again do or picture the exponential function y equals 2 to the power of x, and then what the inverse of that, which would be log base 2 of x, what that would look like. So if I pick just some sample values of x to use, so picture -2, -1, 0, 1, 2, and maybe 3, the values of y that I would get there are 1/4, 1/2, 1, 2, 4, and 8. So if I picture reversing that, so again we're looking at the x and the y's here. So if I just exchange the x and y in each case, the coordinates I will get for my base function, the log base 2 of x function, will be as follows. Right, so we'll start out by graphing the base function, and then literally all we will need to do is translate that up 3 units and be done. So once we have the points from the table plotted, it's just simply a matter of connecting them with a smooth curve. So the function I've plotted to start is log base 2 of x, and then to produce the function we were asked to graph, simply all I need to do is translate each of those points up 3 units. So if I do that quickly now, I will have a function that looks as follows. So the graph there, as far as what we could show the equation as, we could write the original equation or the transformed sort of alternate version of the equation we decided to use. Now the one thing that would be not necessarily plotted accurately with the way I decided to graph this ends up being the X-intercept of log base 2 of x plus 3. We could sort of figure that out if we had pictured where we would have been at when we were at the equivalent of, if I go back to the original table, so if I had actually included for x being -3, picture that would have been at 1/8. Then I would have had a point at y equals -3 in the inverse, which would have been for an x value of 1/8. So technically, if I wanted to know exactly where the x-intercept to that function is, I would have just needed a few other points from my original table to work with, so we could pinpoint where the x-intercept of that function would need to be. Wasn't asked of us though, but it is something worth mentioning. So as far as the domain, range, and asymptote, as we've been doing, so the domain in this case, notice the domain will not have changed between my original base function and the function I was asked to graph here, in that I did not have to translate this function horizontally. So I still have x needing to be greater than 0 and any real number. Range, again, not much ever changes with the range, in that it will be all real values. And my vertical asymptote is x equals 0, which is the y-axis. Next example. So we're going to need to approach this question sort of in a similar way to the last one, in that at first glance, with this particular function, it might be somewhat complicated to picture how we would graph this. One other thing we have not seen to this point that sort of makes this example unique, at least at this stage, is inside our brackets here, there's not just an x, there's actually an x squared, which is not something we've ever had to deal with before. So what I would suggest we do here is, again, picture, are there any logarithmic laws we're familiar with that would maybe make the simplification of this expression possible? Now the fact that I am actually looking at division here, so x squared over 16, what I could incorporate that might simplify this is actually the quotient law. So what we'll do is we'll rewrite the equation as y equals, so our base is 4, so log base 4 of x squared, and then because I'm doing the quotient law, I have to do the difference of log base 4 of what my denominator was, which in this case was 16. Right? Now as it turns out, because we're working with a base of 4, 16 is actually a power of 4. Right? One other thing to consider, the fact that I have x squared as the argument of that first logarithm, what I could actually use now is the Power Law of Logarithms, which says I can actually take that exponent outside of the logarithm and multiply it as a coefficient in front. So this would become 2 times log base 4 of x, and I'm subtracting log base 4 of ultimately 16 is 4 squared. So now, fully simplified, my equation could look like 2 times log base 4 of x, and then log base 4 of 4 squared would just be 2. So with my equation written like this, it is now a lot more clear what the actual transformations will need to be, which we'll get to momentarily. So as far as the function we might want to picture to start out with here, again, if we're starting with the exponential, which is always a good idea, it would be 4 to the power of x, and then the base function we want to work from is log base 4 of x. So if I pick just some specific points to work with here within my table, so if I went -2, -1, so these are sort of typical values to use, and then corresponding y values to go with them. Now we may not be able to fit all of those points in the table because clearly they get very large as I get past 3, even at 3, and then when I do the switch of the x and y values, I will get the following table. Okay, so we've got our base exponential and then the corresponding inverse base that we will want to graph to start with. And then if we picture transformations that need to occur here, and the function we are going to need to transform is log base 4 of x. So as far as what we would need to address first, we would need to address stretches first. So in this case, my stretch will be a vertical one, so I would have to stretch vertically by factor 2. And then I would also have to consider, well, the -2 at the end of the equation would be a vertical translation, so I'm going to have to translate down 2 units. Right, so we'll start out again with the base function and then perform the transformations in the order listed. Now one issue with this graph is going to be I'd have to go all the way over to 16 horizontally to be at 2 vertically. So I'm going to picture, just a rough estimate, I'm going to be way off of the actual grid here when I try and graph that. So I'll just know when I get to x equals 10, I should not be at 2 vertically here. So when I sketch this, something like that would make sense. Right? So that would represent the graph of log base 4 of x. So now picture if I was to vertically stretch that function by factor 2, what would happen? Now the one point that would actually not move is my x-intercept, so that's going to stay in the same spot. The function so picture at 1/4 for x, I was at -1 vertically. If I double that, or stretch it by factor 2, I would actually be at -2 at that point. Right? The point where I'm at 4,1, if I stretch that vertically by factor 2, I would be at 4,2. Right? And then similarly, if I pictured where that point was roughly, if I doubled its y coordinate, I would have to be up here at 4 vertically. Right? So when I make the connection of these points, there would be the equivalent of 2 log base 4 x. Right? And then the last thing I need to do with my graph is to take the one in green, translate it down 2 units, and we would have the graph completed. So each of the points I've currently plotted, if they move down 2 units, I will have the function graph. So notice roughly where I'd estimated part of the original function is now actually part of my final graph as well. So now I would have something looking like that as my final curve, my function in red, to log base 4 of x minus 2. And then to wrap up, my domain and range and vertical asymptote will be provided. Okay, last example for today. Now this one is similar to the previous question in that we again have a ratio or a rational expression involved within the argument of the logarithm. One difference here is I no longer have an x squared, so that will likely mean no stretch vertically. However, the location of the variable in this case is actually the opposite to what it was before. In the last example, it was in the numerator. In this case, it's actually in the denominator. So, like in the previous question, we're going to picture, okay, well, I could use, again, the quotient law to simplify this. So this would become log base 3 of 27 minus log base 3 of x. Now, as it turns out, 27 is a power of 3. So if I envision 3 cubed being the same as 27, and then I am subtracting log base 3 of x, my final equation will look like, now what I'm going to do here is like I did in the previous questions, I'm going to put the expression with the x first, so I'd have negative 1 times log base 3 of x, and then if I had simplified the log base 3 of 3 to the power of 3, that would just be plus 3. Right? So as far as looking at that particular function, we are going to see, because of that negative coefficient out front, it is not stretched vertically, but in the end it will actually be reflected vertically through the x-axis, and the addition of that 3 at the end would imply another vertical translation. So as far as our base function in this case, we start out with the base exponential, which we'll want to take the inverse of. That will be 3 to the power of x. So our base logarithmic function will be log base 3 of x. If I pick, again, your standard x and y values, we can create a table of values. And the inverse of that, again, just exchanging the x and y coordinates. Right? And then if we picture, all right, my base is log base 3 of x, so what transformations will I need to perform of that function? So the first thing I would need to address is this is being reflected, so I'm going to reflect in the x-axis, and then second thing I would need to do to complete the graph is to translate up 3 units. Right, so we will graph our base function and go from there. So with our base function plotted, we now know what two transformations need to occur. So the first is the vertical reflection, so reflection through the x-axis. So what I'm going to do is just take the points that I have plotted to create this function and do a mirror image of them through the x-axis. The one point that will not move happens to be the x-intercept, so it stays put, but each of the other points is now the same distance away from the x-axis, but on the opposite side. I still also have the same asymptote, that has not changed. So there is my graph of y equals negative 1 log base 3 of x, and then I also need to now translate, as we discovered before, up 3 units. So if I take the points that we have plotted, I'm going to move them all up 3. Connect them, and our graph will be complete. So our final graph in red represents negative log base 3 of x plus 3. And we have our graph finished. And to finish off the question, domain, range, and vertical asymptote are listed. Notice that in the last few examples, because there was not a horizontal translation involved, none of the functions had a different vertical asymptote, and their domain was the same in each case. So this sort of reinforces the idea that in order to produce a domain and a vertical asymptote that are different from your standard log-based function, you do need a horizontal translation present. If you have any questions about any of the examples discussed today, please make sure you ask them in class, and have a good evening. Bye now.